Aisha, hello. Aisha, you hear me?
Yes, hocam, I can hear.
Hello, how are you?
I'm fine. You?
Thank you so much. Okay. Aisha, you do not have BNG 211, is that true?
Yes.
Okay, good, good. How many courses do you have this semester?
5 hocam.
What? How much?
5.
5. Okay, good. So, production and reservoir drilling, what are they?
PNG 322,
322,
352.
352,
Yes, and 443.
4, what's that?
It is a TE course.
Mm-hmm. Mm-hmm. Okay, here is Manhaj. Ahmed Sabik, okay. Ahmed Sabik. Okay, guys. How are you? Oh, here's Sultan.
Hello, hocam.
Hello. Okay. Sultan, do you hear me? Sultan,
Yes, hocam. Good morning.
good morning. Would you please give me your ID number? ID number?
Okay. 2345
2345
775.
775. Okay. Okay. So this week I'm going to continue. Okay, here is Bruce. Okay. I'm going to continue talking about Circle Road pumps, but before that, let me, Bruce, good morning. Bruce, do you hear me? I think there is something wrong with the connection of Bruce. Okay. Yes, man, I'm going to give you the permission to record.
Hocam, would you give it also to Shafiq because I'm using my phone?
You are using your phone. Let me see, Shafiq. Okay, Shafiq, you got it. I'm still waiting for Bruce, but I think, okay, Bruce, you got the permission to record now. I don't know why you do not have your microphone with you now. Okay. Okay. So this week I'm going to continue talking about Circle Road pumps. Last week we have started talking about Circle Road pumps, and we talked about the 4 parts of the Circle Road pumps, starting from the prime mover, the part responsible for the power supply, and then we talked about the surface equipment, the crank, the pitman, the workman, and the horse head, the polished rod. We also talked about the rod citron, the pipe that connects the surface equipment with the plunger. The last part, the main part, is the Circle Road pump, the part installed inside the well bore. This part is no more than, let me see, a barrel that could have the reservoir fluid in, and then this reservoir fluid is going to be delivered to the production tubing. So these are the 4 parts of the Circle Road pumps. We have covered also the design of the Circle Road citron, what we need, how can we calculate the stroke per minute, the actual stroke per minute, using the stroke per minute of the polished rod, and the stretch that we could have it either for the string or for the production tube. Well, we talked also about how to calculate the pump displacement, and of course the production capacity. These are all the let me see, the topics that have been covered last week. Now we need to continue. We need to continue talking about the other parts of the Circle Road pumps and the design criteria. We need to finish the design criteria for the Circle Road pumps. So let me share with you my notes. And we have been here. We have reached to we are done with all of that. And I think we have reached to this part. Now we need to talk about the polished rod motion, the polished rod motion, and the calculation that we need to do for this part. Now, when I said polished rod motion, I'm talking about the part of the rod citron that is at the surface. It is not inside the wellbore, no. It is the part that you can see. It is at the surface. Zaid and Diana, okay. Where is Zaid? Here is Zaid. And Diana. Where is Diana? So the polished rod is a part of the rod citron, but this part is not inside the wellbore. It is at the surface. So you can see this one. You can see the polished rod. Here is the polished rod. You can see here is the polished rod. This is the polished rod. Here is the polished rod. See, this is the polished rod. Now, as we know, the socket rod, the mechanism for the socket rod pumps, that the plunger could move downward, get the reservoir fluid, and move upward, deliver reservoir fluid to production tube. So the system inside the wellbore going to move vertically, downward and upward. And the system inside the wellbore is connected to the surface equipment by the polished rod, the one that we are going to see it at the surface. So the polished rod is going to move downward and upward. In this case, because of the weight that we could have, when we move downward, the weight is not going to be the same. I'm talking about the weight of the system inside the wellbore. It's not going to be the same when the system is going to move upward. Of course, the weight when the system is going to move upward is much greater than the weight when the system is going to move downward. So in this case, we do have different, let me say, different velocities and different accelerations. We have the acceleration when the system is going to move downward, and the acceleration when the system is going to move upward. And of course, the acceleration when the system is going to move downward is greater than the acceleration when the system is going to move upward. So we have two accelerations. We have the maximum acceleration, A max, and we have the minimum acceleration, A min. And we can see that when we look at the polished rod. The polished rod is going to move very slowly when the system is moving up. And the polished rod is going to move very fast when the system is going to move downward. Now, the maximum acceleration, as I said, when the system is going to move downward, the maximum acceleration is calculated by this model. So it is S. What is S? The total stroke per minute. And we know how to calculate S. S is S sub P plus the stretch of rod citron and the stretch of the production tube and the plunger over travel. So basically, we are going to calculate S at the beginning, and this is the speed of the pump. Okay, and here's a conversion factor, 17,471 times 1 plus C over H. What is C over H? C over H, these are two characteristics parameters given to you by the manufacturer. They are taken from the characteristic charts of each pump. C is what? C is the distance. C is the distance from the beginning of the crank. Here is where the connection point between the crank and the pitman. Here is the pitman. Here is the pitman. So C is the distance between the beginning of the crank to the connection point between the crank and the pitman. This is C. While H is the length of the pitman, the length of the pitman. So these are taken from tables. I will show the tables to you. C and H are taken from tables. Good. While the minimum acceleration, sure, when the pump is going to move upward, the minimum acceleration is calculated from the same model, except we have 1 minus C over H. Here, 1 plus. Here, 1 minus C over H. So we'll have two accelerations, maximum acceleration and minimum acceleration for the polished rod. The polished rod stroke length, S, here is S, it can be calculated from this model. See, the polished rod stroke length, it can be calculated from this model. This one should be calculated for each one. 2C, and we know what is C, D2 divided by D1. D2 divided by D1. Now, what is D2? Here is D2. What is D1? Here is D1. See? So, D2 is the distance between the fulcrum. This is the fulcrum. Here is the fulcrum. The point at the mid of the workman, the fulcrum. This is called the fulcrum. See? To the horse head. While D1 is the distance between the fulcrum and the conduction point between the workman and the pitman. And these are, these are characteristic parameters given to you by the manufacturers. We can have them from the tables. You can find the tables where in the literature, okay? So these are the way how to calculate the maximum acceleration for the polished rod motion. Okay. Now, when we need to have the when we need to do the calculation for the polished rod loads, you know, I mean, the load is gonna be all the load inside the whirlpool, all the load inside the whirlpool. I'm talking about the load of the equipment, the plunger, the barrel, the rod cistern, and the load of the fluid inside the barrel, and the load of the fluid inside the production tube. All loads is handled by what? By the polished rod. So the polished rod should be selected carefully to have the strength, so it can handle the total load of the system inside the whirlpool. Now, what are the parameters that could affect the total load of the polished rod? Fluid load, as I told you, fluid load. Fluid load inside the barrel, the fluid load inside the production tube, the weight of the socket rod, the weight of the socket rod. I'm talking about the weight of the material, and of course the acceleration, because we need the pump to move at specific speed. We need to have the stroke per minute, so we could have the production capacity at the surface. So the acceleration could have some impact. And of course, we have what's called buoyant force. The socket rod pump going to be submerged in reservoir fluid downhole. Now, reservoir fluid could help, in this case, by the buoyancy force, could help us. You know, the weight of the body inside the water, it is not the same to the weight of the same body at the air. See, the reason for that, we have the buoyancy force given by the water. We do have the same thing when the system totally submerged in reservoir fluid. there will be some buoyant force acting on the system. And the buoyant force in this case is going to work with you. I mean, I'm going to work with the system. And of course, we have the friction forces acting on our system. So these are all the things that we need to consider them when we need to calculate the total load of the polished rod. And again, we are expected to have two different loads. We have two different accelerations, minimum acceleration, maximum acceleration. The same thing we are expecting to have. We have maximum load and minimum load. The maximum load when the system is going to move upward. The minimum load when the system is going to move downward. So the maximum load when the system upstroke, see, upstroke, what would be in this case? The weight of the fluid, WF. The weight of the rod, I'm talking about the material of the rod citron. And the part of the acceleration, that is the weight of the material times the maximum acceleration. We are moving upward. Friction force and buoyancy. So let me show you. In this case, let me see. This is our system. This is our system. See, let me see. This is our system, and let me see that we have some. Here we have. Here is reservoir fluid inside our production tube, and this is our plunger, the barrel. What we have fluid here, and we have what plunger, and we have this is the rod citron. See, the rod citron gonna go all the way to the surface. See, now we have to think about what WF. Of course, WF is going to move downward. This is weight. WF is going to move downward. This is weight. Good. And what we have the weight of the rod citron. This is WR. And WR is going to move downward. See? So this is WF. And this is WR. So we have two forces acting downward. And when the system is going to move up, we have the acceleration, the gravity acceleration that could work downward. This is the part. See, this is WR A max, WR A max, downward. See, A max. See, the weight of the material times the acceleration. And we have the friction. When the system is going to move up, we know that the friction always in the opposite direction the motion. So here is the friction. The only part that could help you, as I said, because the pump is submerged in the fluid, reservoir fluid inside the wellbore, so the buoyancy force is going to work in the upper direction. This is the buoyancy. Here is the buoyancy. See? So when I need to calculate the resultant force, I am going to put all the forces having the same direction minus the forces working in the opposite direction. What are the forces working in the downward direction? WF, the weight of the fluid, WR, the weight of the rod citron, the acceleration part, the friction part, minus the buoyancy force. Guys, is that clear? Because this is really important. Is that clear? Is it clear here?
Yeah,
Is there any question? Is there any question? Is there any question?
No, Hojam.
Good. Now, the plunger is going to move upward. The plunger is going to move upward. Then, when the fluid is delivered to the production tube, the plunger is going to move downward. When the plunger is going to move downward, in this case, there is no impact for the weight of the fluid. because the fluid now inside the production tube, and the plunger is going to move downward. But we still have the weight of the material. We will still have the weight of the material. So the only thing in this case, the only thing that we have in this case, when the system is going to move downward, let me put it here. When the system is going to move downward, there will be no impact for the weight of fluid. So this is our fluid here, and the system is going to move downward. See? So what we will have, there is no WF, but we still have what? We still have WR, the weight of the materials. WR is going to move in the downward direction. This is WR. Now, when the plunger is going to move downward, we are moving with the acceleration, the gravity acceleration, the impact of the gravity. So the impact of the gravity is going to work in your side in this case. See, so the gravity acceleration, I'm going to say, it is going to work with you, against you, but it is in your side. It is against you, but it is in your side. So this is WR min. This case, we are going to go with the minimum acceleration because we are moving downward. And of course, the buoyancy is going to work also with you. See? And when you move downward, the friction going to be upward. So it is going to help you again. So this is the friction. See? See? So now we have three forces acting in the upward direction. And we have only the weight of the materials working in the downward direction. So the resultant force in this case, W min, this would be the weight of the material minus the acceleration, minus the friction, minus the buoyancy. So we know how now we know how to calculate W max, we know how to calculate W min. And this is the mechanisms for the forces acting on the system when the system is going to move downward and when the system is going to move upward. Now, what we need to know how to calculate WF. We need to know how to calculate WR. We know how to calculate I max and I minimum. So this is good. We need to know how to calculate the friction. We need to know how to calculate the buoyancy force. So we can in these two models, and then we will be able to calculate the maximum load on the polished rod and the minimum load on the polished rod. Of course, we are looking what? We are looking for the maximum load, because this is what we have to consider. We have to consider the maximum load on the polished rod. The polished rod should be designed to handle the maximum polished rod. Okay. So is it clear so far, guys? Okay. See, this is the same thing that I already explained to you. W max, this is for upstroke. See, WF, WR, WRAF, buoyancy force, and this is for case of downstroke. So here is the maximum, here is the minimum. Okay. This is what I did. Okay. Now we're gonna have them one by one. As I told you, we need to know how to calculate WF. We need to know how to calculate WR. We need to know how to calculate F, friction. We need to know how to calculate the buoyancy force. Of course, we need I max and I minimum, and we know now how to calculate these two parameters, I max and I minimum, using the two models already explained to you. Now, for the fluid load, we are talking about the total volume of the fluid above the plunger. Above the plunger, where? The fluid inside your production tube. Inside your production tube. Okay. The fluid inside your production tube comes from what? Comes from the length of your production tube, from the plunger to the surface, times what? Times the cross-section area of the plunger. So what I'm saying? So this is the fluid that we need to calculate. Here is the fluid that we need to calculate the weight. the fluid from this point, see, inside your production tubing, where? To the surface, see, here, to the surface here. So this would be what? This would be the cross-section area times what? Times L. What is L? The total depth where the pump is installed. The total depth where the pump is installed. It is calculated from dynamic liquid level D plus the submergency. If it is not given to you L, if it is not given to you L, then you can calculate L from what? If you know the dynamic fluid level, then D, dynamic fluid level, plus the submergency. As I told you, submergency could be 200, 300, 400, 500 feet. It's up to you. This is a kind of tolerance given to you. So we would always be sure that the pump is submerged in reservoir fluid, and there will be the pump off condition. See, we have to be away from the pump off condition. So the total fluid load in this case gonna be calculated from what? Calculated from the volume of the fluid above the plunger inside your production tube. This is volume. And if we know the density, we can calculate the weight of the fluid. But before that, if you look carefully here, guys, let me make it a little bit bigger. Okay, oh, I need to move out. Yes. When we calculate the total volume of the fluid, part of the volume inside the production tubing, part of it is used by the rod citron. See? So basically, we have to remove the volume of the rod citron from the total volume of the production tubing. It is just like this. This is your production tubing. Here is the circle for your production tubing. This is the circle for your production tubing. And there is inner circle for what? Inner circle for the rod citron. So what do you need? You need to calculate the cross-section area here times L. This is what you need to do. Now, the volume of the fluid, as I said, it is the total volume calculated from the total length times the area of the plunger, that is the area of the production tubing, minus the rod volume. Now, what would be the rod volume? The rod volume, if we know the rod citron size, then we are going to go with pi divided by 4 d squared times L. This is the volume. Or sometimes the weight of the rod citron could be given to you by the manufacturer. So it is the weight, WR, the weight of the rod citron, divided by the density of the materials used for manufacturing the rod citron. For example, steel fabricated rod citron. So you have two options. Knowing the diameter of the rod citron, then you can calculate the cross-section area of the rod citron times L. If you do not need to work with this one, sometimes you may have the weight of the rod citron, the weight given to you by the manufacturer, and the type of the material given to you by the manufacturer, the density of the material given to you by the manufacturer, then the weight divided by the density. This would give you the volume, the rod volume. So the volume of the fluid, the total volume times the rod volume. And here is, if it is not given to you, here is the density of the steel. Density of the steel is 490 pounds per cubic for steel rods. Please keep it in your mind. This is ROAS. So WF is what? This is volume. See, this is volume. This is volume times density. Gamma F, the reservoir fluid specific gravity. Reservoir fluid specific gravity times 62.4. This would be the density in pound per cubic feet. And this is pound per cubic feet, rod volume. So we can write WF in this shape. L, the total length from the surface to the depth where the pump is installed. A sub B is the plunger area, plunger cross-section area. And we know it is the size of the plunger times by divided by 4, times D sub P, diameter of the plunger. And this would be 0.94 WR. 294 WR. Okay. Now we know how to calculate WF. Guys, if there is something missing, please let me know. Now we need to calculate WR. What is WR? WR is the weight of the rod citron. As I told you, the weight of the rod citron. L times AR. What is AR? Cross-section area of the rod citron. If we know the diameter, then it will be very easy for you to calculate the weight, the cross-section area of the rod citron. So times L. What is L? The total depth to the pump. Rho S, the density of the material, divided by 144, just to change it to book fit. So this is WR. Now, the problem is when we have tapered rod citron, we have different sizes of the rod citron, Then we have to have the cumulative cross-section area. In this case, what we are going to use, L1, the part of the rod citron where the first size is used, plus L2, A2. A2 is the cross-section area of the second size of the rod citron, plus L3, A3, and so on. Times the density will be the same. We're talking about the same materials will be used, different sizes, same materials. So this is the way how to calculate WR. Now, how to calculate the acceleration load? We know how to calculate Amax. We know how to calculate Amin. Then we just need to multiply Amax by the rod weight. While the minimum acceleration rod, Amin times WR, the rod citron weight. How about the buoyant force?